Hi, in this video, we are going to continue our course on functional equations. So the last class we had discussed some problems where functional equations were solved by solving a system of equations. And today we are going to add the concepts of injective and surjective functions and think about how we understand the nature of the function, whether it is 1, whether it is onto, and that helps us to solve functional equations, right? So we start off with a problem. This is question number 6, continuing from the last class. And this says, given f goes from R to R, satisfies the condition f of 2 power x cube plus x whole square minus f of 2 power 2x is less than equal to 2, and another condition f of 2 power 2x whole cube minus 3 times f of 2 power x cube plus x is greater than equal to 2. We want to show that the function that comes out as a solution which satisfies these conditions is injective, is not injective. Show that this function is not injective or not 1, function, right? So the complicated nature of this argument here, the input to the function, suggests that maybe we should look for situations where 2 power x cube plus x will be equal to 2 power 2x, because that will mean the input to the functions is the same, right? If the function was injective and inputs are same, then f of the function f of a is also going to be equal to f of b, right? If it was 1. So let's find out first the points at which these inputs will be same. So basically this is x cube plus x is equal to 2x and x cube minus x equals 0. So obviously x can be here -1, 0 and +1, right? And whenever x is -1, 0 and +1, the values of these input 2 power 2x can be 1/4, 1 and 4, right? So these are the three different values of the argument that is sent as an input to the function 2 power 2x, and the values of x at which it happens is -1, 0 and 1. So let's call these values as u, v and w. These are sent as inputs to the function, and basically we can say that for any z, that is either u, v and w. What was u, v, w? U, v, w is anything from the set 1/4, 1 and 4, right? For any z belonging to these inputs, the inequalities in the problem will become something like this. So actually, if you give input of z to the function, what we know is that f of z is equal to f of 2 power x cube plus x and is equal to f of 2 power 2x. So z is any one of these inputs, and at those values, both of them are equal because x could have been -1, 0 and 1. So the inequalities become f of z whole square minus f of z is less than equal to 2, and also f of z whole cube minus 3f of z is greater than equal to 2, right? If you look at the first inequality here, you will get f of z whole square minus f of z minus 2 is less than equal to 0. The solution of this is clearly, it's a simple quadratic inequality. The solution is -1 is less than equal to f of z is less than equal to 2 from here, right? If you look at the second one, it becomes f of z whole cube minus 3f of z minus 2 is greater than equal to 0. So now what we can do here is take, if you see 2 is the root of this equation, right? 8 minus 6 minus 2. So we can say f of z whole square, f of z minus 2, and we are getting minus 2 f of z square. So plus 2 f of z into f of z minus 2. We are getting a minus 4 f of z. So we do a plus f of z minus 2 here, right? in order to factorize it, so we are getting f of z minus 2, and inside we are getting f of z squared plus 2f of z plus 1. So that is clearly f of z plus 1 whole square greater than equal to 0. Now, obviously, this is a perfect square, so this is always positive. So what this inequality implies is that f of z is greater than equal to 2, right? So notice that we have f of z can be anything between minus 1 to 2 and also can be greater than equal to 2, right? And both these conditions have to be satisfied simultaneously. So it cannot be greater than 2. So it has to be equal to 2, or it could be, that's it. That is the only possibility, I think. So what we are getting here, there is one more option here. The other option is f of z could be minus 1 actually. This inequality has a solution when the perfect square is 0, right? So f of z could be minus 1 or f of z is greater than equal to 2. So from here and combining it with this first condition, the possible values of f of z are only two values. It could be minus 1 or it could be 2. Anything less than 2 is not allowed by this condition. Anything greater than 2 is not allowed by this condition. But minus 1 is allowed here and it's also allowed here. And 2 is allowed in both the cases, right? So f of z could be minus 1 and 2. Now, if f of z is minus 1 and 2, then we know that f of 1 by 4, z represented what? Z represented the inputs 1 by 4, 1 and 4. So f of 1 by 4, f of 1 and f of 4, all three of them can take only two values, minus 1 and 2, right? F of z has to be either minus 1 or 2. So this immediately implies that three values of the function are going to map to only two outputs, right? So this is a clear many to one function because there must be some two inputs out of these 1 by 4 or 1 or 4 where both of them are mapping to the same output, which immediately implies that since two of these values are equal to one another, it means that the function is not injective. So that basically finishes off the proof that the function that satisfies these inequalities is not going to be injective, right? So this tells us one important thing. Whenever we want to prove that a function is injective, that a function is injective, the equation f of something 1 is equal to f of something 2. This type of the equation becomes useful because for injectivity, if this is true, then we have to be able to equate something 1 to something 2, right? So keep that in mind. This is a pretty common idea when we try to think of injective or such or not injective behavior of functions, right? Let's go to a next problem. Find all functions. Find all functions f goes from z to z that satisfy f of 0 is 1 and f of n is equal to f of n plus 2 plus 2 is equal to n for all n belonging to integers. So this is the condition that is satisfied. Now think about it. What is the meaning if somebody says f of n is equal to n? That automatically means that the function is injective. Function is injective. Why is that? So think that let's assume that f of a is equal to f of b. Now, if f of a is equal to f of b, we can take a function on both sides. F of a is equal to f of b, right? This implies this, and by the condition, this is a equals b, right? By this condition, f of a will be equal to a, and f of b will be equal to b. So that automatically means that A is equal to B is coming as a consequence of f of A is equal to f of B, right? Which implies that the function is injective. So right now we already know that the function that satisfies this condition will be injective, right? Now let's look at other things here. So we have f of n is equal to f of n plus 2 is equal to, this implies that f of n is equal to f of n plus 2. Why am I saying this? Because just now we have figured out that the function is injective. So the output of f when you gave input f of n and when you gave input this are both same. So that means the inputs are same. That means this will be equal to this part, right? So we are getting this condition due to the injective property of the function. So that's why it is important to think about these things. So now that we have got this condition, it is very easy to show by induction. So we have gotten a condition f of n is equal to f of n plus 2. It is very easy to prove by induction. Prove by induction that f of 2m will be equal to 1 minus 2m for all m belongs to integer. How do we do that? It's quite simple. We will assume that we can see that f of 0 is equal to f of 2 plus 2, and f of 0 was given as 1 in the question. So we are getting f of 2 is equal to minus 1 from here. And similarly, we can also see that for the inductive step, we can assume that f of 2m was equal to 1 minus 2m. And in order to prove find f of 2m plus 2, we can do 1 minus 2 times m plus 1 according to, okay, in order to prove f of 2m plus 2 is this, we can say f of 2m plus 2 will be equal to, okay, we will use the condition here to say that f of 2m is equal to f of 2m plus 2 plus 2. And from here we will say that f of 2m plus 2 is f of 2m minus 2, right? And because f of 2m is 1 minus 2m, this can be written as 1 minus 2m minus 2. So that is 1 minus 2 times m plus 1, right? And here I have got it as f of 2 times m plus 1, which is equal to 1 minus 2 times m plus 1. So that proves the induction step. We have assumed this result and we have proved the induction step, right? So we get that for even integers, this is valid, right? Now, given an odd integer, if k was equal to 2l plus 1, we want f of 2l plus 1, right? So now if you think about it, we already have information that f of n is equal to n, and we already know that f of 2m is equal to 1 minus 2m, right? So if I think about f of 2l plus 1, I can say that that is the same thing as f of 1 minus 2 times minus l, right? 1 minus 2 times minus l. So f of 2l plus 1, so think about it. If I do f of 2m, right? From here, if I do f of 2m, that will be equal to f of 1 minus 2m. And this part is equal to 2m, right? So I have 1 minus 2 times minus L is going to be the same as, in this relation, m is minus L. So this is same as f of 2 times minus L, right? Which is going to be minus 2L, right? So using this condition and this relation, we are getting the value of f of 2L plus 1. I will just repeat the argument. F of 2L plus 1, we are saying we can rewrite it as 1 minus 2 times minus L. And we already know that f of n is equal to n, and f of 2m is 1 minus 2m, right? So taking f on both sides here, we get f of 2m is equal to f of 1 minus 2m. But using this condition, this left hand side is 2m. So 2m is equal to f of 1 minus 2m. Now this we will use here, and we will say m is equal to minus L. Therefore, f of 1 minus 2m here will be 2 times minus L. So we are getting f of 2L plus 1 is equal to minus 2L. So what we can do here is just add and subtract a minus 1. So 1 minus 2L minus 1. So this is 1 minus 2L plus 1. So that is my f of 2L plus 1. We already know that f of 2m is this 1 minus 2m, and f of 2L plus 1 now is coming as this. So that means for both even and odd integers, the function behaves the same way. So f of n is equal to 1 minus n in general for all integers, right? For all n belongs to z. And that is what we wanted to show, right? Or that is what we wanted to find. We have found the solution for this functional equation now. So remember here that we use the properties of induction a lot here, right? We use the property of injective functions a lot here, right? A standard way for proving injectivity is contradiction. You should know that. Contradiction method is useful in proving injectivity because we can always assume two distinct elements A1, A2, two distinct elements A1 and A2 in the domain of F and such that f of A1 is equal to f of A2 with A1 not equal to A2. If you can show that there is f of A1 is equal to f of A2 with A1 not equal to A2, then that is a contradiction because that means that the function is going to be not injective then. The same output is coming for multiple different inputs, right? So this is a standard way to try to solve or understand whether a function is injective or not. So keep that in mind. Let's go to the next problem. The question says, find all functions f goes from z to z such that f of x plus f of y is equal to f of x plus y for all xy belonging to z. Okay. Now think about it. If f of a is equal to f of b for some ab belonging to z, what will happen? I will put y is equal to b here, f of x plus f of b. No, I will put y is equal to a here in this relation. And I'm getting f of x plus a, right? Now, if f of a is equal to f of b, the left-hand side here can be written as f of x plus f of b. And that will become f of x plus b, right? So this is equal to this, is equal to this, is equal to this. And these two equalities automatically imply that a is equal to b. So if you start with the assumption that f of a is equal to f of b, you are immediately getting that a is equal to b, which means that f is injective function or a 1-1 function here, right? So now we know that f is injective. Now we will go ahead and try to solve this equation. So let's put y is equal to 0 in this functional equation. We have f of x plus f of y is equal to f of x. The functional equation was is equal to f of x plus y, right? In this, we will put first y is equal to 0. So first step is y is equal to 0. So let's see what comes. F of x plus f of 0 is equal to f of x, right? So because it is injective function, we can say x plus f of 0 should be equal to x, which implies f of 0 is equal to 0. So this is the first conclusion we know because it is injective. Now we put x is equal to 0 in the equation. If x is equal to 0, we are getting f of y is equal to f of 0, which is 0 plus y. So basically we are getting f of y is equal to y. This is the second relationship, right? And now in this equation, you can put instead of y, I will put f of y. So what will happen? F of x plus instead of f of y, it is now f of y is equal to f of x plus instead of y, I am putting f of y, right? And now we know from point number 2 that f of y is y. So this is simply f of x plus y is equal to f of x plus f of y. And this is a famous Cauchy's equation. The solutions of this equation are easy. You can prove by induction that f of x is equal to x times f of 1 is a solution. This is my answer. Basically, it is f of x is equal to kx or minus kx also. So basically, you'll have two solutions. F of x is equal to x times f of 1 or minus x times f of 1. And both of it which satisfy the functional equation f of x plus y is equal to f of x plus f of y. So what we did was using the properties of injective function and using the property that f of y is y, we put instead of y, f of y in the functional equation to get a new version of it, which looked like this. And this Cauchy's equation, it is really easy to prove that these functions will be solutions of this equation. It's a linear function. It's like cx, where c can be positive or negative, and c is basically f of 1. What are the first steps here? Try to do it by induction. So you can put x is equal to 0, y is equal to 1, and you will say 0 plus 1 is equal to f of 0 plus f of 1. Or if you put f of 1 and 1, you will get f of 1 plus f of 1 or 2f of 1. So basically you're getting f of 2 is equal to 2f of 1. Similarly, you can assume that f of x is equal to x f of 1. You will be able to go the next step, the inductive step. So I will leave the details of the induction to you, but the idea is simple that once you get this equation, after that the solution is known, and these are the solutions for this functional equation, right? Okay. Another thing you should realize is if GOF, or basically what we call G of f of x, is injective, then f of x is injective. F of x is also injective. So this is an important property. Let's try to understand why this is not true. This is true, right? So we will suppose f is not injective. Suppose f is not injective. That means there are two different elements, two distinct elements a and b in the domain of f, a and b, such that a is not equal to b and f of a is equal to f of b. So we are assuming that the function is not injective. So now to this, we can do g of f of a is equal to g of f of b, right? We can imply this because we have just applied g on both sides. Now think about it. This is like saying to the GOF function, I have given input a, which is equal to GOF of b. Now the question itself said that GOF function was injective. So this implies what? A is equal to b. And we started off with the condition a is not equal to b and f of a is equal to f of b. So that becomes a contradiction, which means our assumption is wrong. Our assumption was that f is not injective. And now we have realized that f must be injective. So remember this property, if the composition GOF is injective, then f is injective, right? Okay, let's go to the next problem. The question says, find all functions f and g defined from R to R such that G is injective, and f of g of x plus y is equal to g of x plus f of y. And this is true for all xy belonging to real, right? Now, think about it. We are given that g is an injective function. And if g is injective, since g is injective, we will try to make the LHS a constant. We will try to make LHS a constant. You will realize why we are doing it. So for now, to make LHS a constant, one way to do it would be to put y is equal to minus g of x. Because that will make the LHS here f of 0 is equal to g of x plus f of, instead of y, I have put minus of g of x, right? So this is the situation right now. Now, this is a constant now, f of 0, and we are getting the right hand side is a function of x. Now, because g is injective, we know that this value, it cannot be any random real number, like g of something in x, right? Something in x is equal to a constant. Think about it. If there are multiple values here possible, g of a1, g of a2, if all of them were equal to constant, the function would not be injective, right? If there are more than one values here for this expression, then you would have g of something is equal to constant, g of something else is also equal to the same constant, which would be a contradiction because g is supposed to be injective, which means there is only one function. It's only one input to one output, right? So this implies, because the left hand side has become a constant, we can now say that the input to the g function is also constant. The input to the g function can take only one value. If it took more than one value, then g would no longer be injective, right? So that is the idea why we did this step. We will try to make LHS a constant, right? Because on the RHS, we have an injective function, right? So that is a standard trick. Please be aware of this. This will be useful many times. So now what we are getting is f of minus of g of x is equal to c minus x for all x belongs to real, right? This is the condition we have. Now, if you think about it, here the g function here can take all real values, because g and f were both defined from R to R, Here the right hand side can also take all real values, right? Because the x is a variable, it can take any real values. So this function implies that f of something is equal to b, where b can be anything in the real, right? And this was b can be anything in the codomain, right? So you always get some input such that f of something is equal to this. That immediately means that f function is surjective. F is a surjective or onto function because the range here is equal to the codomain. The output or the range of the function can be any real number. Codomain was also any real number, right? So now what we will say is f is surjective. We already know g is injective. Overall, now we can say that g of f is surjective. So the original condition, f of g of x plus y is equal to g of x plus fy. Since f is surjective, g is injective, we can now say that g is also surjective. So let's think about it. Why? So let a be real such that g of a is equal to 0. Now, if I put that x is equal to a in this original equation, you get f of g of a plus y is equal to g of a plus f of y, right? So g of a is 0. So this is becoming f of y is equal to g of a plus f of y, right? Now, f of y, since y can be any real, f of y can be any real, can be any real. And now we are getting g of something which can be anything is equal to f of y, which can be any real. And the codomain of g was also real numbers. Here f of y will also cover all real numbers. So this is like g of a is equal to b, which implies that g is surjective. So g is becoming a surjective function. And if you choose, like your f of y can be anything. So let's choose f of y to be equal to b in a particular case. So that will mean b is equal to g of a plus b, right? And that immediately tells us that g of x is equal to x minus a, right? G of x is equal to x minus a is the solution for g. And using the original condition here, we can even get the solution for f. So we will say now f of g of x plus y is equal to g of x plus f of y. And we have just now figured out that g of x is x minus a, right? So putting that here, x plus y minus a is equal to x plus f of y minus a, right? So we are getting this situation, f of x plus y minus a minus f of y is equal to x minus a. So it is obvious from here that we can write it as x plus y minus a, and we are getting x plus y minus a minus y is same as f of x plus y minus a minus f of y. So it is obvious from here that f of x is equal to x fits. So we have already gotten g of x is x minus a, and now we have gotten f of x is equal to x. And those are the solutions to this functional equation. So this solution also teaches you one important thing, to show for every surjective function, we can replace f of something to an arbitrary number, whenever something can be any member of the codomain. So what we are saying is, whenever you have a situation where f of x equals to b, where b can be any real number and x also can be any number of the domain, then automatically that f is a surjective function. We will see a couple more examples of that. So let's look at this particular problem. So it says find all functions f from R to R such that f of x plus y is equal to 2x plus f of y minus x for all xy belonging to real. Now, first thing to realize is that this 2x can be any real value, because x varies through all reals, can be any real value. So if we want to show that f is surjective, if I want to show f is surjective, I should get an equation something like this. F of a is equal to b, where b can be any real and a will be in the domain, right? So this is the type of thing I need to get to show that f is surjective. So we'll choose a suitable y, choose y such that one of these f terms vanishes. One of these f terms becomes a constant. So that is what we are trying to do, because the other term now will be equal to 2x plus some constant, which will mean that f is surjective. So here, in order to do that, we'll say x is same as x and y is same as minus f of x in this original relation. So we get f of x minus f of x is equal to 2x plus f of minus f of x minus x, right? So this is the situation that we have. And now what we are getting is this is f of 0 is equal to 2x plus f of minus f of x minus x. One second. This was inside the bracket. This was inside the bracket, right? So what we are getting is f of 0 minus 2x is equal to f of minus f of x minus x, right? So imagine this part can be any b, right? Because this is a constant and minus 2x and 2x can be any real number. So this is like your b and this part is like your a, right? F of a is equal to b for any b belonging to the codomain, right? So what this tells us is that f is surjective, right? So we have proved the surjectivity of the f function. Now in the given equation, let's say we have two reals such that f of a is equal to f of b, right? If you put x is equal to a and keep y as y in the original functional equation, you will get f of a plus y is equal to 2a plus f of y minus a. And similarly, if you put x is equal to b and y, keep the y as the same thing, you get f of b plus y is equal to 2b plus f of y minus b, right? So now you can see that because we have said that f of a is equal to f of b, that automatically means that here the LHS of 1, this is 1, this is 2, is equal to the LHS of 2, which implies that we are getting 2a plus f of y minus a is equal to 2b plus f of y minus b, right? So this is the condition that we have achieved so far, right? We are going to hope that this function is injective, because if it is injective, that means this part is equal to this part, right? For injectivity, you will have to say that f of y minus a is equal to f of y minus b. Because if that was so, then 2a is equal to 2b and a is equal to b. And we started off with the condition f of a is equal to f of b, which will prove injectivity, right? So now choose y to be real. Y can be any real. Choose y to be a plus b. If you do that, you will get 2a plus f of a plus b minus a, so b is equal to 2b plus f of a. And that clearly tells us that f of a is equal to f of b, right? Because we know that a is equal to b for injective functions. We have started with the condition that a is equal to b here. So we are getting f of a is equal to f of b from here. Basically, I'm trying to show that it is injective as well. So anyway, in order to solve the equation, we can put x is equal to 0 here. And we will get f of 0 plus y is equal to f of y, right? And this implies that because f is injective, we can say f of 0 plus y is equal to f of y. And that gives you the solution. F of y is y plus f of 0. That is the solution of the functional equation. you can prove that this solution will satisfy the conditions of the problem. And the main idea here in all of this was proving injective and surjective nature of these functions. So keep that in mind while you attempt problems. Before we end the class, we'll talk about a couple more concepts, which is monotone functions. Monotone functions are basically functions that are either increasing or decreasing. Either increasing or decreasing. So the definition of increasing and decreasing functions goes like this. If A1 and A2 belong to the domain and we have with A1 greater than A2, that implies f of A1 is greater than or equal to f of A2. That is the definition of increasing. And if this implies that f of A1 is less than equal to less than equal to A2, right? Then that would be the definition of a decreasing function. This is decreasing and this is increasing. So that is your basic monotone functions. Now, what are arithmetic functions? Arithmetic functions are those which have domain of natural numbers. Their domain is the set of natural numbers. So these are just definitions that you should know. Another important definition is what is an involution? Involution. So we have already seen this condition. It is a function f goes from A to B such that f of x is equal to x for all x belongs to real, right? This directly implies, basically this condition directly implies that the function is surjective. We already did the proof of that. Now remember that if you have f of A to A is an involution, technically f will also be a bijection also, because this condition implies injective and surjective. Surjective because here the x can be all reals and b was, as long as b is the set of real numbers, then it is also surjective. So then this function will become a bijective function. In fact, if you think about it, an involution is simply like a permutation. Different elements as inputs are permuted to give different elements of the same set as the output, right? Obviously, converse is not true. We are saying here that an involution, as long as it is from the set A to A, is also a bijection, but converse is not true. Bijections need not be involutions, need not satisfy f of x equals to x. So bijections do not have to satisfy this condition. We will see more problems on involutory functions in the next classes. We'll also look at some more problem solving techniques which are frequently used. And after a couple of classes, I think we'll move on to the Cauchy inequality, Cauchy's functional equation. We'll see the proof of that. So stay tuned. If you like the content, please subscribe to the channel and turn on your notifications. That way you'll be able to find out if there's a new video released. Also, the links to all my Udemy courses are available in the description. You can check them out. These are courses for Olympiads and also a couple of courses for JEE. So that should definitely be helpful for students who are preparing for these exams. That's all for this video. We'll continue the series in the next lesson, and I'll see you then.